Hello, today we are going to discuss about the reflection and the transmission at normal incidence. Let us consider a light wave which is propagating in positive z direction, and as shown in this figure, let this dotted line separates a two medium 1 and medium 2. That is, when light wave is propagating from medium 1 to medium 2, the medium 1 whose permittivity is epsilon 1, permeability is mu 1, refractive index n1, and velocity is v1. When a medium is propagating in positive z direction, its propagation vector is represented as ki, that is, the incident wave vector ki is denoted in positive z direction, and the corresponding electric field of incident wave is ei, which is in positive x direction, and the magnetic field bi is in positive y direction. In the same way, we can also plot the reflected wave in negative x direction, since we know that the reflected wave is just opposite to that of the incident wave in direction. So that Kr is equal to minus Ki, and it is along negative z direction, and the corresponding electric field Er is along positive x direction, and the magnetic field Br is along negative y direction as shown. Now, when the light is propagating from medium 1 and reaches to the medium 2 of epsilon 2 u2 n2 v2, the corresponding transmitted wave can be represented by using this graph, and the kt represent the propagation vector along positive z direction, and the electric field represent the in positive x direction, corresponding magnetic field along positive y direction. We know that for an electromagnetic wave that is traveling along z direction, whose electric field vector E can be represented as vector E is equal to vector E0 e raised to I kz minus omega t plus delta into x cap. Okay. Similarly, the magnetic field vector B is equal to B0 e raised to I kz minus omega t plus delta y cap. In the same way, we can also write the incident wave, reflected wave, and transmitted wave electric field as Ei of alpha t is equal to E0I e raised to I k I z minus omega I into t x cap, where E0I is the amplitude of the incident wave, okay, field, and the corresponding ki omega I, the subscript indicates that it is relating to the incident wave. And similarly, you can also write the expression for electric field of reflected wave, that is Er is equal to E0R e raised to I k R z minus omega R into t x cap. Okay, here also Kr can be replaced by minus Ki because the incident wave is just opposite to that of the reflected wave in direction. So we are replacing, and the above equation can be written like this. In the same way, you can also place an expression for the transmitted wave Et, as it is equal to E0t e raised to I kt z minus omega t into x cap. In the same way, we can also write expressions for Bi, Br, and Bt. That is, Bi is related to Ei as Ki cross Ei divided by V1. Therefore, on substituting this, we get E0I e raised to I k I z minus omega I into t divided by V1 in positive y direction. The corresponding magnetic field of reflected wave is equal to Kr cross Er divided by V1 is equal to E0R e raised to I Kr z minus omega R into t divided by V1, which is along negative y direction. And on replacing Kr by minus Ki, you will obtain the above expression like this. And similarly, you can also write an expression for Bt as Bt is equal to Kt cross Et divided by V2. Here we are replacing V1 by V2 because the transmitted wave is in second medium. So V1 is replaced by V2, and the above expression becomes E0t e raised to I kt z minus omega t divided by V2, which is in positive y cap direction. But we know that the parallel component of the electric field is continuous. That is, at z is equal to 0, Ei plus Er is equal to Et. Therefore, we can substitute the values for Ei, Er, and Et, and it will be like this. Here we can see that the Kiz is 0, because z is equal to 0. In similar way, we can write Krz is also taken to be 0, and Ktz is also taken to be 0. Then this equation will be written as equation 1. And this should be true all times, irrespective of t above boundary condition should be satisfied. That is, until t is equal to 0. Which implies we can say that when omega I is equal to omega R is equal to omega t is equal to some value, say omega, where omega is nothing but the frequency of electromagnetic wave, and when it is remain unchanged, the above equation, that is equation 1, can be taken as E0i plus E0r is equal to E0t. Why? Let us look at this equation 1. Here you can see this E0i into e raised to I minus omega I into t. Similarly, here is minus omega r into t, and here it is minus omega t into t. When this omega I is equal to omega r is equal to omega t, we can replace it by omega, right? So when this equation consisting of e raised to I omega t plus E0r e raised to I omega t is equal to E0i E0t into e raised to I omega t. Okay, so these quantities got cancelled and the remaining term will look like E0i plus E0r is equal to E0t, and let it be taken as equation 2. We know, therefore, in the same way how we calculate the electric field, we can repeat the same pattern, that is at z is equal to 0, Hi minus Hr is equal to Ht. Here the negative sign indicates that you know that in reflected wave, the Bi in opposite direction to that of the incident wave, and that negative sign just indicates that this direction is changing. Okay. So Hi minus Hr is equal to Ht implies here we know that H and B is related by the equation H is equal to B by mu. So therefore Hi become Bi by mu1 minus Br divided by mu1 is equal to Bt divided by mu2, because the T corresponding to the transmitted wave which is in the second medium. Okay. Therefore, substituting the value for Bi, that is in terms of Ei, the equation becomes E0i divided by mu1 V1 minus E0r divided by mu1 V1 minus E0t divided by mu2 V2. Let it be the equation 3. Now, this equation can be rearranged and can be written like this by including a new term which is called as beta. And beta is taken to be mu1 n2 divided by mu2 n1, because we are replacing v1 v2 as n2 by n1. Okay. So where equation 4 can be obtained like this, that is E0i minus E0r is equal to beta E0t. And adding equation 2 and equation 4, we will get an expression like this. That is 2E0i is equal to 1 plus beta E0t. And write this in terms of E0t, that is E0t is equal to 2 by 1 plus beta E0i. Let it be equation 5. Now substituting this equation 5 in equation 2, we will get E0t minus E0i is equal to E0r. Let it be explained in detail. We just rearranging the above equation in terms of E0r, that is E0r is equal to 2 by 1 plus beta E0i minus E0i. What we have done here, just substituting the value for E0t from the above expression, and we will obtain E0r in terms of E0i as 1 minus beta divided by 1 plus beta into E0i is equal to E0r. So in most of this medium, mu1 is equal to mu2. Therefore, we can rearrange or rewrite the beta expression as beta is equal to v1 by v2 is equal to n2 by n1. In same way, we can also write the E0t and E0r in terms of E0i. That is, E0t is equal to 2v2 divided by v2 plus v1 into E0i, and in same way you can also write the E0r is equal to v2 minus v1 divided by v2 plus v1 into E0i. In order to calculate the reflectance and transmittance at normal incidence, we have to find the intensity of incident, reflected and the transmitted waves. So for that, we have a mathematical expression to find the intensity as I is equal to half epsilon V E0 square. Okay, so in this, using this expression, we can calculate the II, IR and IT as II is equal to half epsilon 1 V1 E0 I square. IR is equal to half epsilon 1 V1 E0 R square, and IT is equal to half epsilon 2 V2 E0 T square. So here you can see that II and IR, that is incident wave and reflected wave, are in medium 1, and it is represented by the subscripts 1, whereas IT is the transmitted wave intensity and it is in medium 2 and it is represented by the subscript 2. Now, using these intensities, we can calculate the reflectance and the transmittance. That is, the reflectance and curve can be obtained by taking the ratios of IR and IR. That is, IR, we can see from this equation that IR is equal to half epsilon 1 V1 E0 R square, and IA is equal to half epsilon 1 V1 E0 I square. On taking the ratios, we know that these quantities will get cancelled and the remaining terms are E0 R square divided by E0 I square. And substituting these values, we will get V2 minus V1 divided by V2 plus V1 the whole square. That is, that can be written in terms of refractive index as V2 by V1 is equal to N1 by N2. Therefore, rearranging this and you will get an expression like this, that is N1 minus N2 divided by N1 plus N2 the all square. In the same way, you can calculate the transmittance T by taking the ratio of IT and II, that is transmitted intensity and the incident intensity. And in the same way, you can consider this equation itself, and you can know that here only half will cancel, the other terms will remain. So therefore, epsilon 2 V2 divided by epsilon 1 V1 into 4 V2 the whole square divided by V2 plus V1 square, that is equal to N2 square by N1 square into N1 by N2 into 4 N1 square divided by N1 plus N2 the whole square. Thus, we obtain the reflectance and the transmittance as equal to plus 1. That is, we can say that the sum of reflectance and the transmittance is equal to 1 indicates that the light is incident normal to the surface. In the same way, we can also calculate the reflection and transmittance and obtain incidence. But now, I hope you all understand this section, and let me start it now. Thank you.